We are on YouTube and being recorded. And session chairs, take it away.
All right, thanks, Leo. Welcome everyone to today's first session, which is on real-world crypto. We'll have 6 talks in that session, and we'll be kicking it off by the security analysis of NIST DRBG, and Viet Tung will be giving the talk. Viet Tung, please go ahead and share your slides.
Can you guys see my screen now? Yeah.
Yes.
So, hi everybody. This is John with Yaobin Shen. So today I'll talk about the security of the DRBG, which is a national standard of random number generator. This tool has been used in numerous cryptographic libraries and operating systems, such as OpenSSL or Windows 10. The security of these systems crucially depend on counter-DRBG, but for a long time, there have been very few papers analyzing it. The security analysis in those papers are, however, very limited and cannot support the claims in the standard. Then in 2019, Woodard and Schumel pointed out that some option in the standard might be exploited, and shortly after, their theoretical observation is confirmed by Connie et al. By some side channel attacks on implementation of counter-DRBG. So the lessons learned here are, number one, we should deprecate some insecure options in the overly flexible standard. And number two, you have to be mindful of some implementation issues. But a big question still remains, that is, if we adopt the recommendations from those 2 papers, then is the patched counter-DRBG secure? So our work gives an affirmative answer for these questions. In particular, we show that the counter-DRBG meets the robustness notion of Dodis et al., which is the standard notion of random number generator. So now let me show you a bird's eye view of counter-DRBG. It is based on a randomness extractor that we call condense that encrypt, or CTE. So underneath the counter-DRBG, there is a state KV, which consists of a block cipher key K and an IV V. Counter-DRBG consists of the 3 algorithms: one to derive the initial value of the state, another to refresh the state if you have new random inputs, and yet another one to generate the outputs. For example, if you have a new random input I and you want to refresh the state, then you will first apply CTE on I. You would then use the counter mode to encrypt the extracted output with the key and IV from the state. And the resulting output will be the new updated state. So the technical core of our paper is to analyze the security of CTE. So this tool is based on CBC mark to extract randomness, but its use of CBC mark violates the guide in the classical work of Dodis et al. In particular, it uses CBC mark multiple times on essentially the same input, albeit with different constant IVs. So at the first glance, if you aim to prove that the outputs are pseudo-random, then we are doomed. To circumvent this theoretical obstacle, we observe that the outputs of CTE will be used to derive a key and IV for the counter mode. And if we model the block cipher as an ideal cipher, then the outputs of CTE only need to be unpredictable instead of being pseudo-random. So we can get around this theoretical issue. So this allows us to start analyzing the security of CTE, but the existing analysis of CBC map will give us only a weak bound. To improve the bound quality, we observe that if you want to predict the output of CTE, because it is basically a CBC encryption output, you need to predict both the key and IV of CBC encryption. And in order to bound this unpredictability, well, it translates to bounding a multi-collision probability on CBC map, which is quite challenging. So in conclusion, our work shows that the counter DRBG is now actually secure. Moreover, we also shed some light on the design of counter DRBG. At the first glance, this construction is very cumbersome, but deep down underneath this ugly cover, it contains quite interesting ideas for getting around the limitation of using CBC map to extract randomness. That's it. Thank you.
Thank you very much, Vito. So we have quite some time for questions. We'll again handle it as having questions on the talk right away, roughly for 5 minutes for each talk, depending on the length. So if you have any questions and are on Zoom, please go ahead and raise your hand so we can address that. John Kelsey has a question.
There we go. Oh, okay, can you hear me?
Yes, John.
Okay, so I like your work a lot. This is very cool. One thing I wanted to point out, I said this in the chat too, the extractor that we use is actually called block cipher derivation function, or BCDF, in the standard. I just thought it was useful to make sure everybody knows that, because otherwise they might be looking for CTE and it's not called CTE in the standard.
I know. So we look at that, but the name is not a very mnemonic, and so we choose a different name because we believe that it describes the design ideas quite well. The other one is it's a reasonable name, but I'm afraid that it's kind of hard to pronounce.
Okay, that was the comment I wanted to make. Thank you.
Yeah. So John, I have a question for you. So yes, I think that you were involved in the design of counter DRBG. And
yeah, it's my design.
You intentionally make it quite cumbersome that way, because initially for a simple design that you had, you couldn't pass the starting suite of NIST. Somehow the entropy was, somehow the randomness was not good enough. And somehow if you tweak the design this complicated way, you are able to bypass that. So it seems that the design here actually the security of counter DRBG both theoretically and empirically. Is that correct?
Well, when we did the block cipher derivation function, I'm having a little trouble hearing you, but when I did the counter DRBG, so that's my design. And the block cipher derivation function was certainly not the result of me having a deep analysis of the attacks. It was me being uneasy with just using CBC MAC directly, and wanting to have the ability also, the other derivation function, also the hash derivation function also has this, wanting the ability to get variable length outputs. We've actually looked later on at allowing just using CBC MAC for instantiating counter DRBG as a more efficient thing, and we've considered that. So that's looking at your paper makes me think about that again a little bit more. So so you're having an impact on what we're doing, but especially in general for these DRBGs, I was very much looking at designing things and then trying to attack them, and if I could attack them, then patching them. So I wasn't really thinking in terms of writing something that I could prove anything about at that point. And you definitely see that in all the designs.
Thank you, John.
All right. Thank you. We have to move on to the next talk, but there is some more questions in the chat. So maybe Virtung, you can take a look at now or later. And also for all the other speakers, please, after your talk, also to take a look at questions which we might not cover in the time given here. So let's move on to the second talk, which will be given by Joel on the security analysis and improvements for the IETF MLS standard for group messaging. Please go ahead.
Thank you. Can everybody see the slides?
Yes, thanks.
Good. So thanks for coming to my talk. I'm Joel, and I'm going to tell you about some joint work with Sandro, Yevgeny, and Yanis. So in this work, we looked at a primitive or protocol called continuous group key agreement. You can think of this as group key agreement, the older primitive, but for dynamic groups with stronger security requirements and much less interaction. So it also comes under the name group ratcheting. You could think of it as the multi-party version of continuous key agreement. For those familiar with that, that was a primitive introduced for the analysis of the double ratchet last year. What kind of features does this protocol have? Well, as I said, it's got to support dynamic groups, which means the group membership can change over the course of one session. Also, these sessions are expected to last very long time, years. So we're interested in security notions that allow for compromise of an ongoing session. For the purpose of this talk, we'll mainly be interested in forward secrecy, forward security, which means that if you compromise a group member today, you steal their local state, this should not reveal old group keys from the past. So the syntax for a CGK is very simple. You can really only do four things. You can create a group, you can add a new member to the group, you can remove an existing member from the group, and you can refresh your key material. It's an update. That's not as important for this talk, actually. Really, the main thing to remember about CGKA is that each one of these operations begins a new epoch in the lifetime of this group. And each epoch is equipped with a fresh group key that should be known to all the members of the group who are members during that epoch and nobody else. So that's what a CGKA is doing. It's giving you this constant stream of group keys, one per epoch. Why are we interested in CGKA? Well, because it's closely related to the messaging layer security protocol. So this is a protocol that's under development by the IETF, collaboration between academia, industry, and it aims to provide an end-to-end secure group messaging protocol. It's supposed to be asynchronous and crucially support very large groups. The thing is, if you look at the MLS protocol, the way it's defined, constructed, you'll find that really the critical novel component in MLS is a CGKA, which is called truncation. And again, its primary function is to provide key material with which to seed a bunch of like symmetric ratchets, basically. So when we want to look at MLS, we decided we're going to start with the truncation CGK. So here are the things we found. First, we found that the forward secrecy of the truncation CGK is really a lot poorer than what we had hoped for. So more concretely, suppose you've got a group of size n. Then each group key is not really going to be forward secure for at least another n epochs after that group key was, after that epoch with that group key. That's really not what you would hope for. You'd hope for that as soon as everybody's moved on to just one next epoch, the group key is already forward secure, i.e. even if you corrupted everybody, you wouldn't be able to recover the group key. So truncation doesn't have this. And what that means for MLS is that MLS is suboptimal in terms of resilience to repeated corruptions. Remember, MLS is also designed for long-term sessions. And so when we say repeated corruptions, I mean something like you corrupt a group member today, and then 1,000 epochs later, you corrupt another group member. It turns out, because of these poor FS properties of truncation, it could be that with those two corruptions, you can recover all the messages that were sent in those intervening 1,000 epochs. And in fact, forward secrecy may never even kick in. It's execution dependent. So with that in mind, we prove a weak security notion for truncation against static and adaptive adversaries. We went on then to look for a construction. We wanted to, fix this problem basically. And indeed, we found a new construction, which we call R truncation. And we show that it enjoys optimal forward secrecy. In other words, group keys become forward secret the moment everybody's moved on to just one more epoch. And we define security, we prove it in albeit in a simplified model where we assume some sort of consistent broadcast. Although we do believe this R-Treecam protocol is secure also in a more general setting, and most of the proof technique will really just carry over. In order to define R-Treecam, we actually introduce a new primitive, which I think is probably, will be interesting in its own right. We called it updatable public key encryption. It's related to similar primitives in the two-party secure messaging literature. And I think of this as forward secure public key encryption light. By light, I mean we relax the notion of forward security that we usually would consider for public key encryption. And what this buys us is truly practically efficient constructions. I'm talking one more group element than an Elgamal encryption. So this is something one can really use. And you can think of this as you take normal public key encryption, and now you augment it so that when you encrypt or decrypt to a key pair, you actually, as part of the process, you're also re-randomizing that key pair. So encryption outputs a ciphertext and a re-randomized public key, and decryption outputs the plaintext and the re-randomized secret key. So how does this play into this problem of forward secrecy for Treecam? Well, think about if you want a ciphertext, you want to say the ciphertext is forward secret, i.e. there's no way left to decrypt this ciphertext. Well, the minimum of what you're going to need to do is make sure that everybody has deleted from their local states the decryption keys. If we look at Treecam, we see that there are actually only few operations that result in people deleting decryption keys, and they really only delete a small number of all the decryption keys that are part of this distributed group state, namely log n out of 2n keys. But what's worse, and this was really the insight that we had, was that these decryption keys that are protecting your target ciphertext, those decryption keys are themselves encrypted under log n keys that are again distributed over the network. So really, you want forward secrecy for that ciphertext. Not enough to delete those decryption keys. You have to also delete those log n other decryption keys. And in fact, this is recursive. Those log n keys are themselves again distributed by log n other keys, each one of them, and so on and so forth. So that's really where the problem rises for Treecam. So what we did is just simply, we said, okay, instead of using PKE, public key encryption, to do your encrypting of ciphertext, you should use updatable public key encryption. Because then what's the result? As soon as you receive a ciphertext, in the process of decrypting it, you immediately re-randomize and overwrite the decryption key. So as soon as you're finished with that, compromising you does not reveal that decryption key anymore. And indeed, following through on that logic, we're able to show that R-Treecam has optimal forward secrecy. Yep. Thank you.
All right, thanks, Joel. We have like a minute or so for a quick question. If you have one, please raise your hand.
There's none in the chat.
Okay, then maybe I have a very quick one. Can you briefly comment on how your new construction relates to what MLS is doing, how the draft is progressing? So are they updating things based on that?
Yeah, so it was, no, they're not updating it. It was a longer debate, and at the moment the consensus is not to take the new construction, but that has to do with engineering constraints with implementing MLS. Essentially, because we're using UPK, not PKE, it means you cannot go to a standard crypto library and simply use its interface, say, libsalt or OpenSSL. You would have to actually, if you want to use the twisted Edwards curves, with NIST curves, you could probably do it with, the Diffie-Hellman basically, but with twisted Edwards curves, you'd have to unwrap that implementation and sort of go one layer below the API to build UPKE. And that was problematic because it imposes a new constraint on implementing MLS that's otherwise not there. So at the moment, that's not going to go into the standard.
Okay, thanks. All right, then let's move on to the next talk, which will be on the paper Anonymous Tokens with Private Metadata Bit, and Michele will be giving the talk. Michele, go ahead.
Hello, hi. So yeah, I will be presenting anonymous tokens. This is a joint work with Ben Kreter, Tancred Lepont, and Mariana Raikova. Anonymous tokens are basically lightweight, single-use anonymous credentials. You can think of them as single-use authorizations. Throughout this work, our work, we focused on secret key tokens. So the same entity that is issuing the token is also the entity that is redeeming them with private metadata bit. What this means is that the issuer is able to embed a single bit within these tokens that can be later read off when they are redeeming the token, and this bit cannot be read by the user. This allows, for instance, for the creation of block lists that are not detectable by the user. More formally, what are we looking for? We have two parties. We have a user, we have an issuer. The user can, during an issuance protocol, ask the issuer for a token, given as input some public parameters and a non-T. The issuer, on the other side, given as input the secret key, and in the case of a private metadata bit, the bit B, can sort of interact with the user, and at the end, the user will get this anonymous token. At a later time, the user can give this anonymous token back to the issuer, and the issuer can check whether the token is valid and extract the private metadata bit from it. We would like these anonymous tokens to satisfy some security properties. Namely, it should be one more unforgeable. The user shouldn't be able to produce more tokens than have been issued by the issuer before. Unlinkable, it shouldn't be possible for the issuer to understand, to link a redemption session with a respective issuance session. In the case of a private metadata bit, we partition the anonymity set with the bit used, and we demand that in the same partition, the issuer is not able to link back the user. And in the case of a private metadata bit, we demand that an issuance session with a bit set to 0 should be indistinguishable from an issuance session with a bit set to 1. These are roughly speaking the security properties that we have. And modulo the fact that the secret key, this is very close to what you could think, for example, for a blind signature. Why are we interested in them? Because on the internet, it is very difficult to understand whether a user is honest or fraudulent, if it's, for instance, a bot or a spammer. And oftentimes on the internet, we have users that try to access some resource, and this resource is finite or is very sensible to spam. What we do in general is that we put an edge server, we put a server in the middle that tries to assess whether the user is fraudulent or not. For instance, by with a login page, which basically destroys the privacy of the user, or with making assessments on where do the requests come from, for instance, on the basis of their IP, which also leads to a lot of false positives, for instance, if with people that are using anonymity services or VPNs. Well, a solution to this is to use these anonymous tokens. Namely, the user can receive these tokens at some point in time when the service can assess the trustworthiness of this user, and then they can redeem them when they try to access this resource. This resource can even be, for instance, a CDN, and our service can be even like a content delivery service. And because of the cryptographic properties of these tokens, it is very difficult for the server to understand which user is redeeming which resource, and it's also very difficult for a user to forge tokens and to lead to a spam attack, to a denial of service. Sorry. Why are we interested in a private metadata? Because if if there is an adversarial user, and this is recognized by the issuer, and the issuer just decides not to give a token, then this could lead to what we call spam learning. The adversary can understand which sort of behavior led to a detection and which sort of behavior wouldn't lead to a detection. And in these sort of cases, what you would like to have is an issuance phase where the server behaves exactly in the same way. So it gives always a token, and within this token, there is a bit, and whether this bit is set to 0 or 1 is indistinguishable. So that's why we have a private metadata. Then at a later point in time, when the adversary tries to redeem this token, well, at that point, we can make assessments based on the bit, and so whether the adversary, for instance, is in a block list or not, and decide what to do with this adversary, for instance, whether to serve the content or not, or whether to take it into account at a later point. And is this really useful in practice? Well, it turns out it is. The W3C, and more precisely, an incubator, the WICG, is trying to push for an API that will be integrated in the browser for issuing and redeeming these tokens. And it's based on another standard, that is being written right now from IETF, that is trying to standardize an anonymous token protocol called Privacy Pass by Davidson and others. And both in both sort of standardizations, there is this idea of having an extension for private metadata, which is what we provide. More specifically, in our contribution to the literature has been to formalize these anonymous tokens and provide a number of protocols that satisfy this private metadata functionality. And we describe also new techniques for the removal of zero knowledge proofs, both in protocols that are being already on the road for standardization, as well in the new protocols that we introduce for having private metadata extension. We also implemented our protocols. They are in Rust, sorry, Kevin. And we published our benchmarks for them so that everybody can sort of see what are the trade-offs, not only between anonymity and functionality, but also with respect to how fast your server needs to be. And speed is crucial in these services because some of the adopters, for instance, Facebook, made public already that they want to use it for advertisement. So I would like to leave you with a couple of resources, like the full talk and the paper and the two standards that I invite you to read. Thank you.
All right, thanks, Michaela. So again, we have a minute or so or two for a quick question. If you have one, please raise your hand. Also, again, the reminder to the speakers, please take a look at the chat. Also, there have been a few questions piling up for previous talks. So yeah, have a look there.
Are tokens always one-time use like Privacy Pass? Yes. Can you describe how the issuer decides whether or not to embed the bit when issuing a token on the user? For example, if this bit determines if a user is on a allowed block list, does the issuer track a user information or to determine? So at issuance time, we always assume that the issuer can understand who is the user. You can imagine, for instance, that if I'm using, I don't know, if I'm using Chromium, I can imagine that the user is logged in on Google, and then Google can give me some of these tokens that later can be redeemed. Or even in the case of Cloudflare, maybe I don't want to tell the user that they are not solving CAPTCHAs correctly. I can just keep on giving them tokens. I just put them in a block list. In this case, they are solving a challenge. And in a certain way, I'm sort of identifying whether they are bots or not. I hope this replies to you, Chelsea.
Oh,
Hi.
yeah, I think the question is more like if these are anonymous tokens, what is sort of the guarantee if you're using additional kind of meta information, even though you're issuing anonymous tokens?
The guarantee of unlinkability is that as long as two persons have the same private metadata bit, then they belong to the same anonymity set. And this is there is a trade-off at play here between anonymity of the user and the functionality that you want to give. And in some use cases, I think you want to play that trade-off. And it's difficult to imagine that some people like, it's difficult to imagine that, for instance, Facebook would, or like some entities would just decide not to, I find it difficult to decide that some people would rather give up on this feature in order to track down a user. Does that make sense?
Yeah, I think that, oh, sorry, I'll let someone else.
We are slightly over time, so maybe we defer this to later. I see there's also more questions on this presentation. There's a little chat, don't miss that one. I'd like to call the fourth paper. This is Aldo Grünsing. Are these the slides? Please screen share.
Yes.
And start. Thank you.
Thank you. So my talk will be about the summation truncation hybrid, reusing discarded bits for free. My name is Aldo Grünsing, and this is a joint work with Bart Manning. So when we look at symmetric cryptographic schemes, we see that a lot of them are based on pseudorandom permutations, or PRPs, like AES, for example. But a lot of them only use the forward directions of the PRPs and do not make use of the invertibility. So instead, we could also use a pseudorandom function, or PRF, instead. And this is actually often more secure than a PRP. The prominent example of this is counter mode. This mode achieves Berkeley bound security of N over 2 bits of security when we use a PRP. but it achieves full n-bit security when we use a PRF instead. So of course, here we assume that we have a perfect PRF, but it still shows that PRF is much more suitable for this mode than a PRP is. So we could try to design a dedicated PRF. However, we have little understanding in how to do that because we are much better in building PRPs based on invertible building blocks. So instead, we could try to design a PRP to a PRF conversion where we build a PRF based on a PRP. So the most straightforward way and very common way is to just use a PRP as a PRF. And this is known as the PRP-PRF switch, which is secure up to the birthday bound. But there are also other constructions like summation and truncation that we achieve beyond birthday bound security. So now we will take a look at those. So first of all, we have summation. This construction simply calls the PRP 2 times and sums their output together using an XOR. And it achieves the full n-bit security. And truncation truncates the output of a PRP to the first A bits, where A can be variably chosen. And it discards the other n-a bits. And this function is also used in the wild, for example, in the key derivation function of GCM SRV. And this achieves n-a/2 bits of security. However, for the truncation, we discard those n-a last bits, but they still may contain some valuable entropy. So we can look what happens when we reuse those instead by applying summation to them. And this leads to the summation truncation hybrid, or STH. And as you can see, it calls the PRP 2 times and just applies truncation to it. But instead of discarding those bits, we XOR them together to get some extra output. And this means that we get n-a extra bits compared to just a truncation construction. But we show that it has equal security to the truncation construction. So we basically get those extra bits for free because we do not have to trade the security for those extra bits. And we also see that it is identical to the summation with our A is equal to 0. So we can actually see it as a generalization of summation. So now I would like to compare those 3 constructions. On the left, we have a graph where that plots the security level denoted in bits against the efficiency. And the efficiency is denoted in the rate, which is the number of input bits on average needed to get an output bit. So the lower the rate, the more efficient a construction is. So first of all, we have the summation denoted by a plus. It achieves the full n bits of security, and it has a rate of 2 because it needs 2 calls to the PRP to get one block of output. And in red, we have the truncation. And when it doesn't discard anything and just keeps everything, it starts in the bottom left. That's just a normal PRP-PRF switch. That achieves the birthday bound security of n over 2 bits with a rate of 1 because it's very efficient. And as we discard more and more bits, the security increases and so does the rate, but that means that the efficiency decreases. And for the STH construction, it has the same security as the truncation construction, but because it is more efficient, it is always to the left of the truncation line. So that was my talk. Thank you for your attention.
Thanks for the presentation. Are there any questions? Raise your hand in the chat now, in Zoom, and speak, or put your question into the chat. Is there anything?
Not in the chat at the point.
And also a hand. So then let me put a question. So I understand that what you're doing is you given a fixed amount of PRP invocations, for instance 2, you try to distill as many PRF bits as possible and prior constructions, and you improve on prior constructions. My my question would be, do you know any asymptotic bounds? So you mentioned counter mode initially, and in counter mode, it's not two invocations that you have, but you actually need a very, very long stretch of PRF bits. So do you think your techniques scale to some specific asymptotics?
Yeah, so here we have the STH construction and we have some input X, but if we would use this in the counter mode, we would first apply it for X equal to 0 and then X to 1 and then 2. And that is also what the security level notes, is how many search blocks you can call before it becomes insecure.
Oh yeah, but you do in this picture, you do 2 invocations of P and you get n minus a extra bits for free. So my question would be, if you imagine you do 5P, kind of, can you over linearly scale the extra output?
That isn't this construction, but you could also look at the such construction. But you can still call it for different X.
Okay, thank you.
We have one question on the ZULIP, which I can read out by Dan Bernstein. The question is sum and truncate more efficient than using a double with PRP?
No, it isn't, because if you have a double with PRP and you just use it directly, you also get n bits of security, but you have to design such PRP, of course.
Okay, we have one more question in the Zoom chat by Yevgeny. Yevgeny, do you want to ask the question yourself? And
sure. Sure. Is there some low bound? This is a really beautiful construction. Is there some low bound that on the best trade-off between rate and security? And if yes, how close is your construction to this lower bound?
I don't know such lower bound, but you also have other constructions that also perform very well. For example, the C-anchor is also decent. But I don't think there are any known bounds about what is possible and what not.
Thank you.
So ideally, you would here of course, be in the top left corner.
So I would like to leave Christopher Patton's question to the ZULIP chat. Please copy that question over, and I would like to Jiayu Shu to unmute yourself and to share your slides and continue with the 5th presentation of the session.
Okay, let me share my screen. Can you see my screen now?
Yes.
Okay, great. So hello, everyone, and thank you for the introduction. Today, I'm going to talk about universally composable relaxed password authenticated key exchange. And this is joint work with Michelle Abdallah, Manuel Barbosa, Tatiana Bradley, Stanisław Jarecki, and Jonathan Katz. So first of all, what is the password authenticated key exchange, or PAKE? So this is a two-party protocol, and the goal is to establish a shared cryptographic key in the so-called password-only setting, which means that the only information shared by the two parties in advance is a low entropy password. So here is a graphical illustration. So this is Ada Lovelace. So she inputs her password PW, and this is Charles Babbage. And Charles enters his password PW prime. And at the end of their interaction, if their two passwords match, then they output the same cryptographic key. And if they don't match, if the passwords don't match, then they output independent keys. So this work is about the security model of PAKE. There have been two major security models for PAKE. One is the traditional game-based model, and the other is the universally composable, or UC model, which is a type of simulation-based security bundles. So as we all know, UC is generally stronger than game-based. And the reason is UC allows for arbitrary protocol composition. and as the name of UC itself suggests. And for password protocols in particular, UC has some additional advantages, such as modeling password reuse. There have been two major paradigms for PAKE protocol constructions as well. So one is you take a regular key exchange, such as Diffie-Hellman key exchange, and you blind the protocol messages using the password. And this yields the most efficient PAKE protocols these days. For example, we have encrypted key exchange, or EKE, and this is the very first PAKE protocol ever proposed. This is in 1992. And there are some subsequent works such as s-PAKE, s-PAKE2, and TB-PAKE. So unfortunately, all of these efficient PAKE protocols were shown secure in the game-based model only, and not in the UC setting. But there also has been no explicit weakness or attack shown for any of these protocols. And on the other hand, there's another paradigm which uses smooth projective hash functions for PAKE protocols. And many of PAKE protocols in this paradigm allows for proving its security in the UC setting. But on the other hand, this paradigm usually imposes extra costs, so it is not as efficient as the first paradigm. So the natural question is there really a gap between efficient PAKE protocols and the UC model? And this is the starting point of our work, and our work is to bridge this gap. So our main result is we define two relaxations of the standard UC PAKE functionality. One is called lazy extraction UC PAKE, or LE PAKE, and the other is called relaxed PAKE, or RPAKE, and RPAKE is slightly stronger than LE PAKE. So the idea of our relaxation is actually very simple. In the standard UC PAKE functionality, it requires that the password extraction must happen before an honest party session completes. And in both of our relaxations, both LE PAKE and RPAKE, we allow the password extraction to happen even after the session completes. And what is the difference between RPAKE and LE PAKE? So the difference lies in what the ideal adversary, or what the simulator learns if it extracts the password after session completes. So in RPAKE, it learns only a bit, which is whether its password guess is correct or not, just as in standard PAKE functionality. And in LE PAKE, it learns a key. So if the password guess is correct, then it learns the real key. And if it is incorrect, then it learns a random key. And secondly, we show that s-PAKE2, TB-PAKE, s-PAKE, and c-PAKE. So these are the most efficient PAKE protocols up to date. So all of these protocols were proven secure in the game-based setting only previously. But now we show that these protocols realize UC lazy extraction PAKE in the random oracle model. So in other words, if you are willing to relax the UC functionality itself a little bit, then these efficient PAKE protocols are all UC secure. And thirdly, we show that UC LE PAKE plus standard key confirmation yields a slightly stronger UC RPAKE. And it also provides explicit authentication. And finally, we also do a sanity check, which is UC relaxed PAKE implies game-based PAKE security with a property called perfect forward secrecy. I believe this was already introduced by a previous talk. And also we show that the slightly weaker UC LE PAKE is also game-based secure, but with a weaker version of perfect forward secrecy. So in other words, this even though UC RPAKE is a relaxation of the standard UC PAKE, it still implies the very basic game-based definition. So there are actually quite a number of interesting open questions, and I only want to mention one of them here. So is UC lazy extraction PAKE really weaker than the standard UC PAKE functionality? And if it is indeed weaker, then in what sense or in what situations is UC LE PAKE weaker? Yeah, so this is the end of my talk. Our paper is on ePrint. You can check it out if you are interested. Thank you very much.
Thank you for the presentation. Hands up in the Zoom if you want to put a question. I see no question on the chats currently. Then let me ask a question quickly. So the old UC model for PAKE is kind of considered a reference model in PAKEs in general, and it is kind of, as you mentioned, it's kind of hard to build protocols that fulfill them, and you are filling this gap. On the other hand, it seems that this was the impression to me that your alternative models are more technical. Do you see that your work will establish like a reference model for PAKE that will be seen as a reference in 5 years from now or something?
To be honest, I really don't know, and I think only history can tell. But of course, my hope is that this UC relaxed PAKE will be accepted as somewhat standard in some years. But I believe before that there must be there are some open questions which must be addressed before that. So for example, as I asked here, so is this UC lazy extraction PAKE really weaker than the standard UC PAKE? So of course, in those efficient PAKE protocols, which are proven secure in the random oracle model only, we have shown basically some separation results, like s-PAKE2 is proven secure in this relaxed model, but it does not seem to realize the standard UC PAKE. But in the if we restrict ourselves to PAKE protocols which are in the standard model only, then is there still a difference between UC lazy extraction PAKE and the standard UC PAKE? So our conjecture is there's no such difference anymore, but we somehow cannot prove it right now.
Okay,
so,
thank you.
So indeed, I believe there are some open questions and was exploring before UC relaxed PAKE becomes the standard.
Okay, thank you. I have one quick question to ask by Scott. Is opaque covered by your analysis? Like maybe not by your analysis, but do you see a problem in analyzing it in your new models? I can give you at most 1 minute to answer, please.
Yeah, so opaque is actually an extension of PAKE called asymmetric PAKE. Here, in this paper, we only analyze so-called symmetric PAKE. So we don't cover opaque. So opaque actually realizes a UC functionality, which is analogous to this UC RPAKE. I believe in the ePrint version of opaque, this is already proven. So actually, opaque is the fact that opaque realizes analogy of this UC RPAKE is one of the motivations of our work on this symmetric PAKE.
Okay, thank you very much. We need to progress.
We're
slightly over time, so the next speaker will be Hao-Wang Wang. Can you share your screen, please?
Hi, can you see me?
Yes.
Okay. So hi, everyone. I'm Hao Yang. I'm going to talk about the malicious framework, embedding backdoors into Twig block ciphers. This is a joint work with Toma. A backdoor of a block cipher should help the one who knows it to break the cipher. And as a designer of the backdoor, we also hope that backdoor should satisfy the following requirement. Firstly, for anyone who doesn't know the backdoor, it should be computationally difficult for him to retrieve the backdoor, even if the general form is known. Secondly, if someone knows the backdoor, then he could use it in an attack and recover the secret key practically. However, there are limited number of works focusing on this topic, especially for embedding backdoors into block ciphers. And as far as we know, almost all designs can't satisfy these two requirements at the same time. Some of them will have already been broken, while the others can provide solid security proof. So in this work, we try to design a backdoor satisfying these requirements. So we propose a malicious framework. This framework is used to build a key alternating tweakable block cipher. And this general structure looks normal, but it has two special features. Firstly, the round function has a partial nonlinear layer. That is, for each round, a part of the internal state will bypass the nonlinear layer and will directly go to the linear layer. And secondly, the tweak schedule used in this framework is chosen XOF, is a generalization of a hash function, and its output can be arbitrarily long. Then the concatenation of the subtweaks will be the output of the XOF. The backdoor that can be embedded inside this framework is related tweak differential characteristic with probability 1. And the pattern of such a differential characteristic over one round is depicted in this picture. The hashed blocks are non-zero difference, while the empty blocks are zero difference. The principle is simple. The subtweak difference delta t is supposed to cancel the difference of a part of the internal state that passed to the nonlinear layer. So the differential transition of the nonlinear layer will happen with probability 1. Then the characteristic will be probability 1. And since this is a backdoor, not everyone can use it in attack. They cannot generate the subtweak difference that is required by the differential characteristic. Actually, this only can be done by a secret tweak pair, which is chosen at the design phase of the backdoor. And we call it malicious tweak pair. So if you know this tweak pair, then you can use this backdoor in attack and recover the secret key efficiently. Lastly, the attacker using the backdoor is under the chosen tweak scenario because only a certain tweak will work. Before I discuss the backdoor security, I would like to first introduce the security notion. We call it target difference resistance. That is, a hash function is target difference resistant if it's hard to find two inputs such that the difference of their output equals to a given non-zero value. And this notion is very similar to a classical collision resistance. And complexity is also the same. That is a birthday bound to the power of n over 2. Then we showed that the backdoor is protected by the XOF. Even if the differential characteristic is publicly known, that is the plaintext difference, the internal state difference, the subtweak difference is all known to the public, we show that it's still difficult to find the malicious tweak pair. Actually, this task is equivalent to the target difference attack on the XOF is used in the framework. That is, given the string of the subtweak difference, the attacker tries to find the corresponding tweak pair, which is input of the XOF. And the complexity could be very high, as we can see here, if we use SHIC 128 or SHIC 256 as the XOF. So next, we propose a concrete instantiation of this framework, and we call it LOMCM. It is a family of tweakable block ciphers directly derived from the block cipher LOMC by simply adding a tweak addition in each round. The size of the linear layer can be set arbitrarily, and the linear layer is a binary matrix, which can be chosen randomly. An instance of LOMCM can have a backdoor or not. So if you want to embed a backdoor inside this cipher, the linear layer that is a binary matrix has to be specially designed. Lastly, the tweak schedule we used in this cipher is SHIC 128 or SHIC 256, depending on the case size of this cipher. We have also discussed several properties about backdoor security of this LOMCM. The first one is that the backdoor is undetectable. As I just said, an instance of LOMC could have a backdoor or not. And we proved that the attacker is unable to distinguish these two kinds of instances. The second is that the backdoor is undiscoverable. It is computationally difficult for the attacker to recover the backdoor. This is because of the target difference resistance of the XOF used in the framework, and the complexity is as high as the cipher security. Lastly, our backdoor is traceable. This is not a desired property because the attack using the backdoor is a chosen tweak, chosen plaintext attack. So once the backdoor is used, it will reveal the values of the tweaks, the plaintext that are correlate to the encryption oracle. So the attacker could use these information to recover the backdoor. For classical cipher security, we discuss it into two aspects. For attacks without using the tweak, we showed that the security of LUMC-M can be reduced to the security of LUMC. And currently, LUMC is very secure now, so our cipher is secure. Then we also consider the attacks based on the tweak, because the tweak input will provide additional frame degrees for attack possibility. However, our cipher use the XOF as a tweak schedule, and because of the property of the XOF, the attacker can't control its output. So we believe the attack can be leveraged, the tweak can't be leveraged by the attacker. So that's all. Thank you.
Thank you. I see a question incoming by John. No, there is actually quite some chat. I see 4 questions. Shah, do you want to just unmute yourself and ask a question directly? Then I read the question. The backdoor can be inserted in the nonlinear layers only, or do we need to mold the linear as well? What is the effectiveness of linear layer in this regard?
Well, the principle of this backdoor is that we want to use the different characteristic just to skip the nonlinear layer. So, and the linear layer, the functionality of this linear layer is to ensure that the different characteristic will carry on through this round and round, and to satisfy this pattern of the different characteristics. So yeah.
So there's 2 more questions of Shafad. I will skip anyway to John Kelsey. If using it didn't reveal trap backdoor, this would be a public key encryption scheme. Oh, that's just a comment. That's not a question. So I have another question for backdoor. Using the backdoor, what is the effort needed to recover the secret key?
Well, the effort is like in 1 second, because the backdoor here is a differential characteristic with probability 1. So you can just use like 1, 2 queries or 3 queries to the oracles. Then you can just do some small computations to recover the secret key. So it's very fast.
So we are over time. There is another 2 questions in the Zoom chat. I would ask the author to copy them over to Zulip. Beyond that, there is another 3 questions by Tom, Dan, and Tim on the Zulip chat, which please can be answered on the Zulip chat itself. I would like to thank all the speakers of the session. The Zulip chat is very lively. Recall that the Zoom chat will not be backed, so this will not be saved. So please, all the important questions be moved over to the Zulip chat. So I thank the authors again. You can send some clappings into the Zoom chat now. Thank you very much.
Thanks everyone for joining.